Hi everyone, welcome back to our channel once again. In this video, we are going to study about Kirchhoff's current law, and this is the very first video of network analysis playlist series. So in this video, we'll study about the basics of Kirchhoff's current law. So the fundamental concept of Kirchhoff's current law says, as per the definition, it is basically the algebraic sum of current entering any node is zero. Now, what do we mean by node? So, node is a point in an electrical circuit where two or more branches meet. For an example, if we let's consider a circuit like this, and we have a voltage source here, and say it R1, R2, and R3. Now, this is the point where you can see the branch 1, this branch, and this. All these three branches are meeting here. It means this is a node in an electrical circuit. Thereby, the another node would be here, here. So three branches, this one, and this. These three meet here, and thereby it's another node. So in this circuit, there are two nodes. Node 1, let's say, and the node 2. So this is about the node. So what is the Kirchhoff's current law says? It says that the algebraic sum of the current entering any node is zero. It means, why is it so? Why the current entering any node is zero? Because as per the conservation of charge, right? A node cannot store, destroy, or generate charge. Thereby, the net current entering any node is zero. Or you can say the sum of the current entering, algebraic sum of the current entering any node is zero. A node is not a circuit element, so it cannot certainly store, right? It's a capacitor can store the charge, a battery can supply the energy, supply the charge, and a resistor can dissipate the energy. But a node cannot have such existence of either storing the energy or generating the energy, or we can say, or destroy, or in terms of, you can say, the dissipation of the energy. So a node cannot neither store nor destroy or generate the energy. Thereby, the sum of the algebraic sum of the current entering any node is zero. Hence, the current must be zero, we can say. So, for example, if we consider the hydraulic analogy, let's say we have a pipe in the form of Y shape. Let's say we have pipe like this, and the water is coming from, let's say, P1, P2, and P3. So we define three currents as flowing into each of the three pipes. Let's say the current, so this one is I1, I2, and I3. So if we want the water flow in through all the three pipes in towards this point, let's, for example, junction, then it's impossible, right? In that, if all the three currents or water will flow from all the three directions, the pipe will burst, right? So it's not possible. It means there would be either one or two side will letting the water going out of the pipe, right? So the direction of flow of current, so one of the direction, either one or two, at least one of the side, the current direction would be different as compared to other. It means all the currents cannot have the direction towards the node, right? And thereby what we say is current entering the node must be equal to current exiting the node. But what we are trying to say is the current, right? If all the three sides cannot have the positive currents, correct? So at least either one or two of the currents must be negative. So therefore, here we can see in this example that I1 is entering the node, I2 is entering the node, I3 is also entering the node. But I4 and I5 have different directions, right? Thereby it is minus I4 plus minus I5 equals 0, right? So the negative currents, basically, you can say the minus I4 is entering the node and minus I5 is also entering the node. Or other way is I4 is exiting the node and I5 is exiting the node. So thereby, if we try to stem this definition out of this, what we can say is The current entering the node equals the current leaving the node. How we can say that? Let these things on the right hand side of this equation. So it is I1 plus I2 plus I3 equals I4 plus I5. And this is very foundation of the conservation of charge, right? Because I1 is what in general, it is the rate of the flow of the charge, right? It is Q1 divided by T, let's say for some delta time T, dq by dt, right? Rate of flow of charge. Similarly, this is dq2 by dt2, and this is dq3 by dt3, which is equal to dq4 by d4 dt4, or and similarly this you can make the time same, will give you the I1 I2 I3 equals I1 plus I2 plus I3 equals I4 plus I5. So what does this say? These are, if you see the direction of the current, I1 I2 and I3 all will have the same direction towards the node. So I1 is entering the node, I2 is entering the node, and I3 is entering the node, while I4 and I5 both are exiting the node. Thereby we can say the current entering the node equals the current exiting the node, and that is the basically Kirchhoff's current law. So if you found this video insightful, stay connected to see more videos and examples on the Kirchhoff's current law in upcoming videos. Thank you so much.